Thank you, everyone. As Isaiah mentioned, I am Keno Fischer, currently a student at Harvard College studying physics and mathematics, as well as being one of the co-founders of Julia Computing. I am Keno on GitHub. You might have seen me around or on the mailing list, or maybe you've seen my JuliaCon talk last year. And you can reach me via email at either of those two email addresses. Now, it's tradition at JuliaCon to talk a little bit about how you got started with Julia. So I want to take a couple of minutes just to tell you how I got started with Julia and why I am now working on a C++ interface, because that wasn't the plan. All right. All right. So 4 years ago, I was in high school, and I took the first ever online MOOC in machine learning. And that's the cute logo they have. And they used Octave. And the class was great. I learned a lot. But I was really frustrated by all the vectorization that was going on. You know, I'd write the problem as straightforward as I could think of, like use a bunch of loops. And then I'd wait a minute for the answer. And then I'd spend an hour optimizing, like 6 reshapes, 5 rep mats. And then, you know, with 6 times the memory and 5 times the float, suddenly it took 20 milliseconds. And that just didn't seem right to me, so I had that thought in the back of my mind. And then a couple weeks, the next semester, so this was the fall semester, then in the spring I participated in this competition called the Mathematical Competition in Modeling, where you have 96 hours, you get a problem, you have to do research, you have to write a program to do the modeling, and then you write a paper on it. And this is a university competition. We were in high school at the time. But I wrote the code in Octave, and same problem. Like, the performance was just terrible. And you know, usually I can stand terrible performance, but if you have 96 hours and are sleep deprived, like, so frustrated, right? So at that point, I decided I would like something better. And I was playing with the idea of improving Octave for a while. Oh, this is, by the way, one of the figures of the paper as part of that competition. The problem was compute the total mass of all the leaves on a tree. So we had a bunch of outlines of scanned leaves and basically grew the vein patterns to estimate for the different leaf geometries how many veins, because they have most of the mass. So this was one of the papers, and this was in Octave. So at that point, I was really frustrated with Octave. So I was playing with the idea of improving Octave. But luckily, just 2 weeks later, why we created Julia, I saw it on Reddit, and I read the article and was like, yes, exactly. That's what I need. So I started working on the Windows port because I tried to download it, and I was on Windows at the time, and you know, it didn't work. So the rational thing might have been to start a Linux VM and try it out. But no, I was a high schooler and had too much time. So I started writing it on the Windows. Started writing the Windows port and started sending cryptic messages to Julia Dev about why the hell isn't this working on Windows. So Stefan picked up on that, and 2 weeks later sent me an email and was like, "Can you put up the code? We'd like to see it." So that was the first source release of Julia on Windows. And 2 weeks after that, Viral was, all right, next month we need a binary release. So, you know, spring break was coming up, and it happened. So that was a bit of the history of how I got involved in Julia, and now how I got involved writing a C++ interface. So well, that wasn't planned. Base. All right, great. All right, so Windows work took until January the following year. And at that point, I had been accepted to Harvard and had finished the fall semester. I didn't do much during the fall semester, lots of math to learn. So I didn't do much the fall semester, but the spring semester, I took Harvard's Introductory Operating Systems class. And you know, if you've ever done low-level operating system writing, you know that debugging it is really, really frustrating. Like, and this was a very primitive version of GDB, like no hardware breakpoints, like, ugh. And I just couldn't stand not knowing what was going on, so I decided I needed some more insight into the system. Now, again, the rational thing might have been to write a few GDB scripts that do this for you, but no. I had been on the Julia train for a year now, had spent so much effort on it, so it had to be Julia, right? So I wrote a bunch of packages. I wrote the elf package, the dwarf package, the REPL package, and the ncurses package instead of doing class work. And the result of that was this little tool, which uses ncurses to draw a representation of memory and disk of the operating system. And then you can see here, down here is a mini REPL. That was the REPL package. And all of these terminals are connected to the same Julia instance, and just basically show you all that's going on. So that was the origin of the REPL package. So Harvard CS161, can't recommend it enough. Right. So that was the origin of that package. So now, like the semester afterwards, we get to the beginning of cxx.jl. So you can see all the work I've ever done in Julia is procrastinating from actual schoolwork, because I think that maybe 3 years later, I might be able to do the schoolwork marginally faster if I have this infrastructure. All right. So next semester, I take the graduate version of operating systems, and I have this really cool idea for a debugger that uses LLVM instrumentation and machine learning to do some really cool things. Only problem being LLVM is written in C++, and I want to use Julia, so need to call it C++ from Julia. So the rest of the semester is spent making the initial C++ cxx.jl prototype working, and by the end of the semester, I did have a functional prototype. Even the beginnings of the LLDB interface, which will become the Julia debugger, and I did manage to use it to complete the class project. Of course, I spent like a week on the class project and a semester on cxx.jl. So apologies to the professor and my group mates who had to suffer under that. But I think the result is still very favorable. So I've been working on cxx.jl ever since, and the debugger, and also behind the scenes, as part of that I've been making sure that once we switch to LLVM 3.7, everything will work fine. So this is LLVM upstream commits. I've been doing a lot of fixing things in LLVM and making sure they work nicely for Julia. And there's some more work to do, but that's what I've been doing since. All right, so this is sort of the end of the history part. From here on out, it's all demos. And beyond this point, there be dragons, because it's going to be a lot of compiler hacking. All right, and I need a REPL. So what's the pit over there? All right, let's see. All right, let's hope this works. All right, great. REPL magic, by the way. I wrote the REPL, so I can do stuff like that, like taking over another terminal, which is running on a different machine and connected as a REPL. Perks of writing the REPL. All right. All right, great. cxx.jl. What is cxx.jl? cxx.jl is the Julia C++ interface. And if you saw my talk at last JuliaCon, I sort of explained this. So last JuliaCon, basically still the prototype I had from the end of my graduate operating systems class. And I demoed some functionality. And basically, the day after, it was obsolete because we implemented staged functions. So I had to rewrite the entire thing. So this is what I'm showing off now. So this is, if you were at last JuliaCon, this will look very familiar. So you do using cxx, and then you can parse some C++ code, and then you can, there's a cxx macro that sort of punts on syntax a little bit and allows you to call C++ functions. So a very simple example. So what did I do since then? So what happened when I did using cxx? Well, before we had Julia sitting on top of LLVM, and now we have Julia still sitting on top of LLVM, but cxx loaded a copy of Clang into memory, also sitting on top of LLVM, and Julia and Clang are communicating through staged functions and LLVM call to generate a bunch of code, and then they both go down to LLVM, and there's cross-language inlining and all of the fun stuff you want for no overhead calling of C++. All right. So this is all old news. You all saw this last JuliaCon, so I'm not going to spend a lot of time on it. So what did I do? What did I do since then? Well, the biggest thing probably is the implementation of these string macros. One of them is cxx string, which parses a C++ string. So you're thinking, well, that's not very impressive. You spend a year doing that. Like you could do that with cxx parse at last JuliaCon. And that's true. You could do this, but it has a lot more features. And I'm going to show off the rest of these features for the rest of the presentation. All right, so this is remember the simple struct. I'm going to come back to it again. It has an int and a float, and it has a print method. And you can create a new one, like, oh, that was my hello from earlier. OK. OK. This is not working. Give me 1 second. All right. They are. Technically, that wasn't supposed to happen. All right. All right, never mind that. Yeah, this is somewhat unfortunate. Let's see. All right. Well, true. All right, let me restart this. My apologies. All right. See, it's very cool when it works, but sometimes it doesn't. And I tried it like 3 times today to make sure it does work. But of course, it only ever goes wrong during the actual presentation. All right. And I need to go back and where was I? Oh, yes, it's down here. Retake control of that terminal, which is 8167. All right. Hopefully, this will work better. All right. All right, not going to use that. All right, ignore that. Sorry about that. That worked. That worked before the presentation. All right, so just going to use the notebook instead, and maybe I'll use the REPL later. OK, so I'm actually going to switch out of presentation mode because I do need to write some code. All right. See, there's a kill-stop in here, which is supposed to suppress bash, and it does. Oh, it did before, but.
Can you use the font size here?
Yeah. All right. OK. I'm going to open a REPL later and show off the cool stuff. But for now, let me just do it in the notebook. So here's what we were. And that's not very impressive. You all saw that last time. So let me make sure this was evaluated. Yeah, so I apologize for the technical difficulties. This talk used to work, and then I upgraded Julia, and nothing ever worked again. Which is OK. This is all unstable, Julia, LLVM, every package. But it's annoying when giving talks. And while that's executing, I am actually gonna prepare a copy of Julia. Okay. All right. The notebook isn't working, but I'm just gonna use the REPL, and this time an actual REPL, not a hacked out REPL on another computer. Well, it's still on another computer, but it's not hacked, so at least Bash shouldn't be fighting over it. All right. All right. I'm just going to do the same demo in the REPL because for some reason the notebook doesn't like it. So using SI units, and we're going to do x is 1 meter, y is a millimeter, and then we're going to define a C++ function. Actually, let me make that full screen. All right. All right, what was it? All right, yeah, x is a meter, y is a millimeter, and now we're going to splice. Now we're going to splice the result of x divided by y as a float 64 into this expression. And this isn't string interpolation, this is semantic interpolation. All right, so it figures out that this is a float 64, and then it splices this expression. So it doesn't like evaluate it and make it a text and do that kind of stuff, but it actually splices the actual value into the AST here, rather than doing some sort of text substitution. And this is all great, so we can have substitution of Julia values, but it suffers from a problem which I like to call the XKCD problem. Because if you try to do this, get random number of rand 0 to 10, what you end up with is that, right? Because you splice the result of rand 0 to 10. So your random number will be fairly chosen by a pseudo-random number generator, but not be particularly random. And you can see that you can see that if I just do @cxx get random number, it's always the same one, 5 in this case. All right, but that wouldn't be any fun. So I actually do have a solution to this problem, which is that you can splice an expression. So instead of splicing the result of a Julia value or global or whatever, you can put a colon in front of it, and then every time C++ gets to this point, it will call back into Julia and evaluate this expression. And that actually does do what you would expect. So really, you get random number. It was 5 the first time. That was just random chance. So you can see calling it multiple times, you actually do get different numbers. And the way it does that is it calls back into Julia to actually get you the random number. So that's great. So what happened there? Well, we have LLVM, then we have Julia, then we have Clang, and then I do a bunch of fancy transformations to pretend to Clang that the Julia function is really a C function and set everything up correctly in LLVM, such that when LLVM goes to find the definition of what I'm pretending to it is a C function, it actually goes and compiles the Julia function. So that was a little tricky to figure out, but it actually works very well. It actually works very well. All right, and that is basically the basic functionalities of the CXX string macro. So you can splice in values, you can splice in expressions. You can do one more thing, but I'm going to show you later what that is, because I don't want to spoil the surprise. Instead, I'm going to spoil a different surprise. Another feature that I added is instead of just having these pesky string macros and the pesky cxx macro, I wrote the REPL. So of course, there has to be a C++ REPL mode, right? Oh, I didn't define my struct. What was it? Yeah. When I had this prepared, they were the same instance, so this struct was available, but now they're not. All right. All right. Yeah, there we go. So, well, actually, this is a great opportunity. This was all planned. You get Clang errors inside the C++ REPL. So if you type something wrong, it's not bad. You just get a nice error, and it tells you what you did wrong, and then you can fix it. So this is a live C++ REPL. You can put any C++ expression in. 1 plus 1, for example, the most exciting C++ expression I could think of. But what I really want to show off is that the result of 1 plus 1 is available to the Julia REPL. So the values are shared between Julia and C++, right? So it's just one REPL backend. The front-end processing is just different. And of course, C++ values are also available to Julia. Now, I look at that and I think, that's great, but I really don't like that printing, right? The printing is just ugly. Well, luckily, we had a print function for foo, right? Where was it? That's both the surprise. All right. Import-based show. And again, I apologize for the technical difficulties. This was a lot more smooth in my practice talk. But so we have a show function, so we can easily define show of foo. So let me go up and grab one of those, and show ANS does not work. Well, that's odd. Why is that? Well, two reasons, and for those of you who've used Julia a lot might have picked up on that. This show function is very odd because it doesn't have an I/O argument, right? The reason it didn't show up here is actually because that was already compiled, so it didn't like it. But all right, so this is odd. So I don't like that, right? There's no I/O argument there. So can we fix that? And the answer is yes, we can fix that. We have the technology. So to do that, all we have to do, very simple, is get C++ to somehow think a Julia I/O object is really a C++ I/O object. How hard could that be, right? So I went online to try to figure out how the C++ I/O interface works, and was directed to this 200-page book that describes it all. But I didn't read it, and instead I figured out how to do it anyway. And because the interruption cost me a bit of time, I'm just going to copy this. I was just before I was going to type it out in real time because it's really cool. Yes, I misspelled. All right, great. So we're going to create something called a class, Julia I/O buff, which inherits from standard basic stream buff, which is, as I figured out, the way that you represent an underlying I/O device in C++. And we're going to give it a private field, which is a Julia object. It's the I/O object. Then just a simple constructor that takes the I/O object and stores it. And this is where all the magic happens. And this is the one other feature that the cxx string macro has, which I implemented just 3 weeks ago. And took me a week, so it's really hard. So, so what this does is you want to declare this member function of this class, and then you want to call the right function in Julia, right? You want to interface from C++ I/O to Julia I/O. And to do that, though, you need to get access to variables in the scope of the C++ member function, right? These arguments are not globals. Like so far, we've seen like evaluating a few expressions and referencing a few globals. But that's not actually the case for these, because they're actually in the scope of this enclosing function. And this was a limitation that bothered me for a really long time until I figured out how to do it. And the way I do it is I actually rewrite these to C++ lambdas, which have the inner expression as the body, and then Clang figures out which variables to capture and figures out all the scoping. And then all I had to do was write a bunch of templates and a bunch of staged functions that then get Julia to evaluate C++ lambdas. But yeah, so it works very nicely. So let's trace through what this does. So it calls write on this I/O, which gets translated automatically back to a Julia object. And then it gives it the s and the length. So the way this function works is you get a char star and a length, and you're expected to somehow write it down out to whatever your underlying I/O device is. So great. So with this, and you can see my notes that I'm supposed to show off the REPL. You wouldn't have seen this if this were the actual presentation, but so it goes. All right, so now we can write an actual show. We can write an actual show method, right? We create a Julia I/O buffer, which takes this I/O object as a JL value t, puts it in here, and then we create a standard O stream, and we can print it. So let me show if that this actually works. So let me go back to here. Oh, it's the other way around. Right? All right. So here's our new here's our new print definition. You can see semicolon in the C++ REPL, by the way, works the same as the Julia REPL. And the other thing is, yeah, it works the same as the Julia REPL. So I had to leave off the semicolon to actually get it to print. So you can see it used our new base.show definition, and whatever crazy I/O device, it's probably an I/O buffer that the REPL has somewhere internally. We just wrote a small adapter that bridges the interface, and now we properly get it to print. So this was the print definition in the struct foo earlier. All right, great. Blah blah blah. There you go. Sorry, what does what? Oh, of course. Right, it's a C++ pointer, right? It's just it translated the type into Julia, and then Julia's multiple dispatch figures out how to show it. So, sorry? Do I ever free the struct? It's on the stack. Yeah, so I do. The compiler does because it's on the stack. All right, great. So I'm going to show off why I use this, because all of this, like messing around with standard streambuff, I only do that for demos. The real reason that I use this and that I wrote it is LLVM. So here's a small helper macro that gets me a Julia function as an LLVM pointer to the appropriate LLVM function, and now we can go to town, right? We can do dump on that expression, and it dumps out that, or we could write like this is really why I use it. I use it to debug CXX itself. So add code LLVMF foo and a dump, and this isn't quite what I wanted, but I can still show this off. So extern LLVM execution engine star JL execution engine, right? So I'm now loading symbols from the Julia binary itself. Find function named Julia foo. All right. So for those of you that didn't catch what's happening here, this is basically my most used command in Julia nowadays. because I trace through how LLVM does codegen, so I need to look at the LLVM representation of a bunch of different functions without even knowing what Julia function they correspond to, just any function. So what I do is I do JL execution engine find function named, and that queries the currently running JIT LLVM, the LLVM JIT, for the function named Julia foo 22426. That's why I use this. It's probably not as exciting as some of the other things you can do with it, but it's extremely useful if you're working a lot with LLVM. I have it right in a REPL, which makes me a lot more productive. So before I go on, I want to talk a bit about wrapper generation, because wrapper generation is generally the alternative, or rather is traditionally what is used to interface with C++. So why don't I like wrapper generation? Like, why didn't I just write a Swig plugin that generates me this? And the reason I don't like wrappers, and I've always hated wrappers, and the reason is they always end up limiting you. So you end up trying to force one set of APIs onto a different set of APIs and hopefully automatically figuring out how to do it, but it's never quite the same, and it doesn't quite work. And because it's not the same, you end up having to write a different set of documentation and tutorials, right? There might be a wonderful documentation for the C++ side of things, and then somebody has the Python wrapper, and because Python doesn't really work the same, the Python wrapper works slightly different, so something that works perfectly fine in C++ doesn't end up working in Python, so you end up writing two sets of documentations and two sets of tutorials, and users get frustrated because it doesn't work. And also, I think they're really unnecessary, because there's literally no work involved, so the system should just do it automatically for you. Like, if it can automatically generate wrappers, it should be automatically able to bridge this problem. And the two things that are really problematic with calling other languages are syntax and interfaces. And syntax is the easy part, and interfaces is the hard part. And generally, the two get mixed up, because you want it to sort of feel native, so you bridge interfaces, but because of all the wrapper generation, you also end up having to bridge syntax. But the only real part where you have to put any thought in is actually bridging interfaces. And what do I mean by bridging interfaces? Well, one language might have one set of interfaces for expressing a certain paradigm, like a graph or an image, and another language might have a different one. And you sort of, if you want the library to feel native, you sort of need to bridge that. And we saw an example of this with the C++ I/O and the Julia I/O object. Obviously, it was a very minimal wrapper, but what it did was it bridged the interface from Julia I/O to C++ I/O by allowing something that uses the C++ native I/O interface to work with anything that implements the Julia I/O interface. And what I showed wasn't really exciting. I wrote to the REPL, but you could imagine loading the GNU-TLS package, and suddenly everything that knows how to write to a C++ object can communicate over HTTPS, right? Because HTTPS would implement the Julia I/O interface. So by bridging interfaces, you really get the promise of modularity across languages. Because that's a big problem with all sorts of using libraries in other languages, is that you have modularity in your own language, and then you have a very thin interface, and modularity just goes down the drain, right? But I'm really hoping that with a richer set of interfaces, you can actually retain this modularity. And finally, the other thing that bothers me with wrappers is they end up incomplete, and if you extend the wrappers, like you generate the wrappers and then you go in and change something, the next time the C++ library evolved, you either have to go in and change it again, or in most cases you just abandon the wrappers completely. So the takeaway from that rant is bridge interfaces, not syntax, and try to maintain modularity across languages. All right, that was my rant. Oh yeah, one more thing to show off is meta-programming with C++. So this is a macro that generates a bunch of Julia functions that implement the standard iteration interface. in C++ or in Julia from the standard iteration interface in C++. So you can see in basically indexing, get index, size, length, and it just assumes it iterates from 1 to size. This is very useful. A lot of C++ objects implement exactly this, so you don't want to write out all of these again. And just to show off how it works, at list, well, include vector, of course, first, and then at list, and you give it a C++ type, and this is a rather complicated type, so rather than using the standard way to declare types, I'm actually using cxxt, which tells Clang to parse the type and give you back the Julia representation of it. I don't like to use it as much because it means that just to parse the thing, you have to have a working Clang compiler. Like all the rest, you can parse without having Clang in memory, which I think will be helpful later for static compilation. But for now, it's using this, and you can see I generated a list, and then I called the Julia generic collect on the standard vector, and it gave me a bunch of references of C++ objects, just because standard vector returns references rather than the actual values. But the cool thing here is I called collect on a C++ object, just worked. I didn't have to do anything special, right? So this is what I mean by bridging interfaces, right? I bridge the iteration interface from C++ into Julia. All right. Now for a demo of science. All right. So last time I gave this talk was at well, not this talk, but a version of this talk I gave at supercomputing, and after the talk, I got a question that was like, so this sounds like a great tool for compiler hacking, but where's the science, right? And it's like, I'm in physics, I can fix that. So using cxx.jl for science, aka how to pass off your homework as a conference talk. All right, so in particular, I'm going to show you how to wrap an existing C++ library using cxx.jl and like become productive really quickly. Like, I mean, you've all seen this, right? You want to do something new, and there's a C++ library for it, but nobody has written a wrapper. So I had this situation last semester. I was taking a class at Harvard in the standard model of particle physics, and we had to use the C++ library called Pythia, which is an event generator for high-energy physics. So basically what it does, it simulates a bunch of particle collisions and then gives you all the data of how that collision worked. So to understand the standard model, we were supposed to use this library to do a bunch of simulations. So that's exactly what I'm going to do right now. So first of all, the boring stuff, just loading a few packages, and then with any binary dependency, you have a bit of setup, right? Like deps.jl and getting a few directories. And something that's peculiar to cxx.jl is you have to DL open the library first with RTLD global, because Clang looks for symbols in the global namespace. And it got changed recently, or maybe it got changed back again, I don't know. But at some point, DL open would do the private symbols, and that doesn't work. So at some point in the future, maybe I'll do something more fancy, maybe with CXX modules to tell Clang, oh, if you found the symbol in this CXX in this C++ module, it'll be in this library. But for now, without like any good separation of which header which library belongs to, it's really not feasible for me to do anything else. So for now, you have to do RTLD global. And then, of course, this is a C++ compiler, so you do have to give it the header directory. So it doesn't save you from that. So let me open this. All right, great. All right, and now I can go on. So I'm going to include the headers, which are in Pythia 8, pythia.h. Great, now using namespace just to make it a little simpler. Right, so at this point, so this is what I actually did when I had to do this in class. Right, I downloaded the library, figured out how to build it, And then I followed the online tutorial, and these were the first 2 steps. So I was like, great, put them in my C++ REPL, and everything worked great. Then at the next step, you have to create an instance. I just called it Pythia, and here's the new Pythia. Well, when I did this last semester, at this point it crashed because Pythia had a bug, and nobody ever ran it like in an address space that was full of random objects. So there was a bit of uninitialized memory. And because there's so much else going on in this address space, it crashed, even though it hadn't crashed for anybody else ever before. But I reported that bug, and 3 hours later, I got back to this. But just imagine if it didn't have a bug, I would have been here in 20 seconds. All right, so we created the instance. And I'm going to set a few parameters for the simulation. So we're going to do proton collisions at 8 tera electron volt, and we're going to enable this particular QCD process. It's an event generator for high energy physics. It simulates particle collisions, like at the LHC. Right. I know I'm almost out of time, but I do want to show this demo. So give me 3 more minutes. Right. All right. So we're going to initialize it, and yay, it initialized itself. Great. And the way you actually work with this is it exposes sort of a stream interface. So you call Pythia next, and it runs a simulation, and then it prints out all the particles. So great. So we've now collided protons at 8 tera electron volts right in this room. So that's great. So it exposes this interface where you can generate event after event. So basically, it's an iterator interface, right? It's an infinite iterator, but it's an iterator. So let's put an iterator interface on it, right? So I wrote this very simple iterator. It doesn't do much. It basically all it does is call Pythia.next, and then there's a bit of post-processing to make sure that if Pythia had an error, it just ignores it, because that happens from time to time. All right, so let's use this. And I apologize for going so quickly through this, but I want to get to the gist of the demo. And I'll put the notebook online, and you can study how all of this works exactly. But I'm going to create this, and I'm going to also create a show method for the event. And you can see here's our good Julia I/O buff again, right? Because this Pythia exactly implements this, right? It uses this C++ standard I/O interface to do its printing. So the same class we created before works here too. And now we do like first events, right? And now we have a Julia interface to creating events in Pythia, right? Just by using iterators. And iterators are fun because you can do a bunch of things. And to show that off, I'm first going to have to actually do this, because you can iterate also over events and give it a particle, and it implements the C++ standard iteration convention. So the macro we created earlier generates the iterator for this just fine. And now I'm going to do my homework, right here in front of you. All right, so the homework was generate 10,000 events. So iterators take events. I need to do using lazy first. All right. So data equals. So the homework was generate 10,000 events. So usually you'd write a loop or something. Oh, that's 100,000. We would have been here all day. So the homework was generate 10,000 events. Then look at all the particles. So I put a pull request to iterators that asks this concat, which just given an iterator of iterators, it concats all the child iterators into one long list. So generate 10,000 collisions, look at all the particles that happened, that occurred, and find only the ones which are final. So that means so Pythia internally keeps track of all the intermediate particles. So it has like a tree of decays. So we were only supposed to look at the ones that actually came out in the end. So we filter only the ones that are final. And you can see there's C++ in here again, mixed with iterators, right? So that's great. And then for all of those particles, look at their ID and name and mass. So we're going to create a tuple that's ID and name and mass. And the byte string here automatically recognizes standard string and converts it to a Julia string. So great. So now it should be going, right? Now it's colliding protons and giving me events. So there's 1,000 events. And this was my homework right live in front of you in 10 seconds. Maybe a little more if I talked about it. But yeah, so I want to again point out, like, I wrote very little code that interfaced with C++. And then I was able to use the generic iterators to do all of my data processing, right? I was able to use lazy to pipeline it. I was able to use the generic take iterator. I was able to use concat. I was able to use filter and map. And basically, literally, the sentence that the professor said was like, generate 10,000 events, look at the final state, and then look at ID, name, and mass, right? So one sentence description of your homework, one line in the code. At least theoretically. All right, and we're going along generating a bunch of events. And I know I'm out of time, but this is basically the last command I'm going to run. Well, not the last command. I forgot using gadfly. But you can and warnings. And I can't actually scroll in this terminal. But if you looked at the output, you can see there was like 1,100,000 particles generated. So it worked. And now we're going to plot them once gadfly is loaded. I apologize. The using gadfly was at the beginning of the notebook, but not in the REPL. So we're going to have to wait. Oh, great. All right. All right. Plot. This is going to take some time. There's 1 million data points. So yeah, but while this is running, I'll take a few questions because this might take like 20 seconds. So yeah.
Back when you were interfacing, I don't know if you could do it in the scrollback history of this terminal buffer here, but when you were interfacing to the stream buff,
Yeah.
you had to capture certain values for Julia.
Yes.
I noticed the C++ expressions all started with return.
Right.
There's other ones that don't seem to need that.
Yeah.
What's the status there?
Very good question. Very observant. That is exactly the right question. So the top-level CXX expressions do cross-language type inference. So it infers all the Julia expressions that get spliced into it, and it infers the return type of expressions, and then it passes it off to, oh, hey, the plot finished. All right. All right. I'm going to talk about this plot in a moment. But yes, exactly the right question. So in general, the top-level ones do cross-language type inference. So it infers the Julia types, and then it passes it off to C++, and it uses the C++11, C++14, C++17 automatic type deduction functionality in the C++ compiler to extend the type inference through C++. So basically, expressions involving C++ are in general quite well typed. And that also generates efficient code, but it also allows you to save a lot of overhead in typing, because otherwise you'd always have to annotate types everywhere. The return is part of that, because as part of that processing, I also walk the AST to insert return expression on the last statement, so that your C++ functions basically feel like Julia, because you can just repeat as you would in Julia, you just write the local variable that you want to return on the last line without return statements, and the last expression gets returned implicitly. This doesn't yet work for the third-level nesting that I showed off in interfacing with stream buffs, because the way that works, as I mentioned, is it actually inlines a bunch of lambdas, and I don't have access to the AST for the lambdas to do this processing before it gets to Clang. All right, and I should probably cut off, but I'd be happy to explain everything afterwards. And this is the plot that was generated. So you can see there's neutrons and protons around 930 GeV, and then there's a bunch of massless things, mostly photons, and then we have a few pions in the mix as well. All right, so that's the demo. I had one more, but we didn't get to it because of technical difficulties. So maybe I'll save it for next JuliaCon. All right, thank you very much.